Hey, I'm Zhang Xin, and I'm excited to present you our work, Spanning Training Progress, Temporal Dual-Depth Scoring, TDDS, for Enhanced Dataset Pruning. You can find our paper and codes on the following links. In recent years, explosively growing datasets have been crucial for the success of deep neural networks in various applications. However, learning from large-scale datasets is both time-consuming and financially prohibitive. A good news is that a substantial portion of data samples are redundant, which means they can be excluded from training without compromising performance. So this is the background of dataset pruning being proposed. Dataset pruning, also known as coreset selection, and aims to enhance the training efficiency by constructing a coreset S that can achieve comparable performance to the original large dataset U. Currently, most of pruning methods rely on the snapshot-based criteria to identify the representative samples, which leads to poor generalization across various pruning settings. Firstly, the importance scores of samples fluctuate with epochs during process of training. Consequently, the coreset constructed by the importance scores at different snapshots of the training progress differs from each other significantly. As verified in this figure, the coreset constructed at epoch 10 and epoch 100 obviously contain different samples. Secondly, relying on importance scores from a snapshot can lead to overfitting in construction of the coreset, as this approach may not generalize well across different scenarios, such as varying pruning rates. As shown in the Figure 2, the accuracy gap of the coreset from different snapshots becomes larger as the pruning rate increases. To address these two problems, a straightforward approach is to consider a broader range of training dynamics throughout the training process, with a focus on selecting well-generalized data samples, like previous works, AUM, and forgetting. Unfortunately, the averaging downsampling operation they use to cover the broader range of training dynamics can inadvertently lead to the neglect of the well-generalized samples during the selection, finally degrading the overall performance. In this paper, we proposed the temporal dual-depth scoring pruning method designed to effectively balance and address the aforementioned problems. We employ a dual-depth temporal scoring metric that spans the training process for the data selection. The pipeline of our proposed TDDS is clearly illustrated in this figure. In the following slides, I will introduce you the implementation details of our TDDS. Following the problem formulation in the gradient-based methods, which propose to minimize the distance between the full dataset and the coreset gradient, JS tilde can be regarded as the gradient reconstruction in the coreset space. According to the previous discussion, we propose to extend this to a continuous training duration to capture the training dynamics. However, directively solving this problem is NP hard, thus we turn to its equivalent, temporal gradient variance maximization. And this is also how our outer level is defined. Our outer level measures the variability of samples and enhances the identification of well-generalized samples. In the previous definition, sample-wise contribution can be evaluated as the variance of gradient magnitude. However, as illustrated in this figure, the gradient of sample xn remains constant between t and t plus 1. However, when incorporating it into the current optimization context, its validated contribution undergoes a significant shift. Thus, we propose to calculate the gradient variance after projecting it on the accumulated direction. Here are some experimental results. As you can see here, none of the compared methods surpass random at aggressive pruning rate, while our TDDS can surpass random by 1.69% and 7.83% after pruning 90% samples of CIFAR 10 and 100 respectively. For ImageNet 1K dataset, when pruning 90% samples, TDDS still achieves 53.91% accuracy, which is 1.77% and 1.46% higher than forgetting and moderate respectively. Thanks for your time. You can find more details in our paper and GitHub repository.